Hello and welcome back to PC Retro Programmer. In the previous video we started to look at assembly optimization for the 8088 CPU with a view to using some of these optimizations to speed up line drawing code that we've written on the channel. Now I made a list of potential optimizations. The first one is pretty generic and could apply for any programming language, but from there down to use lookup tables inclusive, these are the most important assembly optimizations for this CPU. If you use these, then probably you're going to get a fast result. From there's a few others that are more specific that just apply in certain circumstances. So far we've got down to push pop in the previous video, so let's start with the next one, which is related to short jumps. Now you might already be aware that there are a few different kinds of jumps on this CPU. There's the ordinary jump instruction JMP, which just jumps from the current location to a label somewhere else in your program. And then there are the so-called conditional jump instructions. Those will only jump if a certain condition holds based on the values in the flags. For example, JC is jump on carry. This will only jump if the carry flag is set. JZ is jump if 0, JNE jump if not equal, JA jump if above, and so on. There's lots of these. Now the ordinary jump instruction, JMP, also comes in a couple of different varieties, and you don't normally notice this because the assembler usually takes care of this for you. The first version is a so-called short jump, and this takes an 8-bit displacement as an operand. Now what this does is tell it how far to jump from the current location, and the assembler typically works out what that displacement should be depending on how many bytes of machine code away your label is. But this is very limited. It's an 8-bit signed value for the displacement, which means that you can only jump up to 128 bytes back and 127 bytes forward from the current location. Now, if you've got a long program, you might want to jump further than that, and fortunately there's another version of the jump instruction which takes a 16-bit displacement value, which will allow you to jump anywhere in a 64K block. And if you want to jump even further, then there's a so-called far jump, which will take a segment and an offset and allow you to jump anywhere in memory. So obviously each of these instructions takes more bytes of machine code than the previous one, and they take longer to execute. So if possible, you want to use short jumps wherever you can. Now, if you use the conditional jumps, these are all short jumps. There are no longer versions of these. So if you want to jump further than an 8-bit displacement, then you need to use a trick. So essentially what you do is you replace your conditional jump instruction with one having the opposite condition, and instead of jumping to where you want to go, you just jump over the next instruction. And the next instruction will be an ordinary jump instruction, which jumps to where you want it to go if the condition did hold. Now, of course, that's pretty complex and a little bit unfortunate because of the cost. And you certainly don't want to be doing this in a time-critical piece of code if you can possibly help it. So eliminating these long jumps is actually pretty important, especially when you're using these conditional jumps. And the best way to do it is just to rearrange your code. Maybe it's possible by rearranging the blocks in your code to make all the jumps in your program short, or at least all the ones that occur in time-critical parts of the program. And so this is a very important optimization. It's not always possible, but if you can do it, then you're going to get a pretty important improvement. The next thing on the list is loops, and we already know that the loop instruction is the fastest way of doing these on this CPU. The way it works is you put a count in the CX register, that's the number of iterations that you want to do, and then you have a label marking the start of your loop, followed by the loop body, all the instructions that you want to execute every iteration, and you finish off with the loop instruction, which takes as operand that label name that you want it to jump back to every iteration. Now, this is a pretty complex instruction. The way it works is it decrements CX and then it checks CX to see whether it's reached 0 yet or not. If not, then it jumps back to that label that you specified, and if it has, it falls through to the instruction following the loop, and the CPU just continues execution from there. So that's a lot of work for one little instruction. And by the way, it does all of this without affecting the flags, and that'll be important in a moment. Now, obviously, given that this is so fast, you want to use it wherever you can instead of all the other assembly language instructions that you'd have to replace it with. Now, we already mentioned that in the case of nested loops, you'd certainly use loop on the innermost one because that's where you can save the most time. But it turns out there are a couple of other instructions that can do even more than loop. They'll do everything that I just described exactly the same way, but they also bomb out on another condition, and that condition is the 0 flag. In the case of loop E, it will only perform the loop as normal if the 0 flag is set, otherwise it will bomb out. And the loop NE will only perform the loop as normal if the 0 flag is not set, otherwise it will bomb out. So this gives you an additional reason for the loop to end. Now, the way these are usually used is after a compare instruction, or basically anything that will set the 0 flag. Remember, loop itself doesn't touch the flags. So the prior comparison instruction might compare its two operands, and if they're equal, then this instruction would perform the loop as normal. If they were not equal, then this would bomb out. And obviously this would just do the opposite. If they're equal, then it would bomb out. So this allows you to do a loop plus an additional check as well. So very powerful instructions if you can use them. I've never used them personally, and I just realized today one of the reasons I've never used loop E or loop Z is they're actually described incorrectly in the assembly language book that I have. Now, the other thing that's important to know about these loop instructions is they're always going to do at least one iteration. And in fact, if you start off with CX equals 0, then it will do the one iteration, then the loop instruction will run, then it will decrement CX, which will make it FFFF, and obviously it's going to do one hell of a lot of iterations. So what do you do if you don't want it to do any iterations if CX is 0? Maybe the loop counter is actually set as a result of some computation and it can actually be 0 at the start. Well, that's what this instruction is for, something I only really realized today. This instruction will allow you to jump to a label if CX is 0. So you can actually put this before your loop to exclude the case where CX is 0. So that's a very useful trick, and in general all of these instructions are much better than the alternative instructions that you'd have to put in their place. So they can save you a lot of time. But the most important one is to use loop wherever you can instead of conditional jumps. Now, these instructions all unfortunately only do short jumps, so that's something you have to bear in mind, and it's not always possible to use them for that and for other reasons. The next thing on the list is string instructions, and we've dealt with these previously on the channel when we went through the instruction set. These are almost certainly some of the most powerful instructions on the CPU, so you really have to use them if you can. Now, I won't go into these in a great deal of detail since we've covered them before, but these are single byte machine code instructions. There's a byte and a word version of each depending on the last letter of the mnemonic. And there's one for loading a byte or word from memory into the accumulator, for storing from the accumulator into memory, moving from memory to memory, comparing the accumulator with memory, or comparing memory to memory. And these instructions don't take operands. Instead, the memory addresses are specified by the SI and DI registers, depending whether it's a source location or a destination location. And obviously the memory-to-memory instructions are going to use both of those, whereas LODSB is only going to use a source location, STOSB is only going to use a destination location, for example. Now, these instructions get a lot of work done, for a single byte of machine code, but even more with a rep prefix. This is just another byte of machine code that would go in front of these, and it's almost as if you have a loop. Basically, it would just repeat the operation over and over again, a number of times specified by the CX register. And not only does it decrement the CX register every iteration until it reaches 0 and then stop, but also these instructions increment the memory locations, the SI or DI registers, depending on which are being used, by either 1 or 2, depending on if you're using byte or word operations. So for example, you could use rep MOVSB to move a whole pile of bytes from one location in memory to another. Now, sometimes you have overlapping buffers, and instead of copying forwards, you want to copy in reverse order from the top of the buffer down to the bottom. And for that, you can change the direction flag, and instead of incrementing the addresses every iteration, it'll decrement them instead. Now, the first three are used a lot in graphics, but the latter two are more often used in string manipulation, as far as I can tell. These are the comparison ones. But of course, those you want to bomb out on some additional condition, not just when CX reaches 0. For example, you might be looking for a match with the value that you have in the accumulator, or you might be comparing two memory locations and you want to stop when the two blocks of memory no longer match anymore. And for that, you need to bomb out on some other condition, and this is what rep-E, or rep-Z as it is in some assemblers, and rep-NE or rep-NZ are for. Basically, they look at the 0 flag. So you're doing a comparison here, and if the two values compared equal, then rep-E would cause this instruction to stop straight away at that point. And the rep-NE will cause it to stop if they no longer match. So if you were looking for the first point in two buffers where they differed, then you'd use rep-NE. Now, the other instruction is xlat, and this is not a string instruction, but it's a table lookup. You have a base address in the BX register for the start address of your table, and you have an offset into that table given by the AL register. Now, of course, that means you can only have a table of up to 256 bytes, but this can be enough for some graphics effects. If you're looking up some tables of sines or cosines, maybe you're doing a plasma or something like that, then for a single byte of machine code, you can basically get the byte in the table at that location into the AL register with a single xlat. So this can be very powerful and very fast as well. And so if you can use these instructions, you really must if you want a very fast assembly language program. The next thing on my list are the optimized assembly instructions, which I have covered before, but it's nice to have them all in one place in a single list. These are the instructions where Intel managed to save a single byte of machine code in each case. And this is important on the 8088 because we know each byte of machine code takes 4 cycles to load. So the first lot of instructions include all the simple arithmetic operations, the ones that run in 4 cycles essentially. It includes all of the logic operations and or an XOR, and the comparison instructions comp and test. And you'll save the byte of machine code if the first operand can be the accumulator and the second operand is an immediate value, so some constant number basically. And by accumulator I mean either AX or AL here, depending if it's an 8 or a 16-bit operation. Now this is important to remember because if you can rewrite your code to use the accumulator more often than some other register, then that's going to give you a saving every time you hit one of these, and that's going to be quite common. The other place where this optimization works is when you're moving the accumulator to memory or loading it from memory. But here the memory location has to be constant. So essentially every time you access a variable in your data segment, the assembler will be able to figure out the constant offset of that variable. It's a 16-bit offset within the data segment, and it would put that 16-bit offset here, and so long as you're using the accumulator, either AL or AX, that's going to save you the byte of machine code. Unfortunately, you can't use this with all of those fancy addressing modes of the CPU. In that case, you don't get the 1 byte of saving. So the heuristic here is that a lot of instructions work faster with the accumulator. And if you don't remember anything else, it's worth remembering that. It's not the case for all instructions involving the accumulator, but for very many of them. Now, the other case that Intel sped up by 1 byte of machine code are certain instructions, which you can see here, using a 16-bit register as operand. So increment and decrement are already fast, but if you're using a 16-bit register, then that will go 1 byte shorter. In fact, the whole thing is just a single byte of assembly language in this case. Now, the other one is exchange, and it might look a bit odd here because I only have one operand, but the other one is implicitly the AX register. This is a 16-bit exchange only, and so it's only exchanged with AX. It doesn't work similarly as fast with AL, unfortunately. And so depending on your assembly, you may have a different syntax for this. Some of them require you to put the AX in, either as the first or the second operand. Other ones just require the single register that you're exchanging AX with. So just look into that. And yeah, all of these are really worth using if you can, because they're saving you 4 cycles at a time on the 8088, which is definitely worth it. The next thing on the list is to avoid multiplication and division instructions where possible. These are by far the longest running instructions on the CPU, unless you do something silly like use a shift with a very high bit count, for example. So 8-bit multiplication is something like 70 cycles or thereabouts. 16-bit multiplication will be around 130 cycles or thereabouts, and division may be 25% longer than those. And so this is something you want to avoid if possible. There are some algorithms where you really just can't afford to do any multiplications or divisions. Now, when you're multiplying by a constant, you can replace it with shifts and additions. Obviously, shifting to the left is multiplication by a power of 2, and if you add a bunch of these shifts together, then you can multiply by an arbitrary constant. And there are also some tricks to combine shifts and subtractions as well to get it even faster still in certain cases, and I'll probably make a video about that at some point since it's worthwhile. Getting rid of division can be a bit harder. On faster CPUs, division is a lot slower than multiplication, so very often you can replace a division by multiplication with a pre-computed inverse. This is something I know a bit about, but unfortunately on these CPUs there isn't much difference between these, and so this technique just doesn't work out very well. So I don't think this is worth covering. Obviously division by a power of 2 is just a right shift, and there's a whole science of fast division by certain other constants. But the common way of getting rid of division is to use a lookup table. And this brings us to the final topic for this video. It doesn't just apply for division, but basically any function where you need the output for only a small range of inputs. Basically, you just compute that function for all of those inputs and put the values in a lookup table. And quite clearly, reading a value from memory is much faster than running a division instruction, and probably a lot faster than computing some complicated function. But it's a trade-off. If you have a large lookup table, you're using a lot of memory, and if you pre-compute it and store it as a hard-coded table in your program itself, then your program's actually going to be larger on disk, which might not be desirable. And if you don't do it that way, well, then you have to pre-compute the table while the program is running, and so that adds pre-computation time, which may slow your program down overall. On the other hand, you might not care if there's a few seconds of pre-computation, which makes the subsequent effect that uses that table much faster, then it's definitely worth doing. So those are the trade-offs that you make here, and we will use a lookup table for our line drawing. It's not going to save us a lot of time there, but enough to make it worthwhile, at least in the lead-in code. and we'll look at that in a later video.